Okay, hi everyone. So in this presentation, I will discuss about our recent numerical study in quantifying the influence of planetary magnetic field on ion escape rate. So this study is similar to previous one, except that we are using current Mars situation, try to answer the question of the effect of planetary magnetic field. So the model we used here is also a multi-species MHD model that was first developed for Mars. Of course, the main advantage of this model is its ability to self-consistently calculate the ionosphere. As we all know, the ionosphere is the main source for the planetary ions to be lost in space. Our Mars model has also been applied to Venus and Titan and compared with multiple spacecraft observations. As example, on the right, I'm showing data model comparison for one of the strongest ICME event observed by MAVEN. As shown here, there's a fairly good agreement between data and our model result for plasma density, velocity in three directions, strength of the magnetic field, and the three components of the magnetic field. Also, I do want to mention that we do have a more advanced model, which is the multi-fluid model, our newly developed MFPE model, but we are not using those models here mainly because of the large number of simulation runs needed for this particular study, but we do plan to rerun at least some of the cases to verify the findings of this study. So here I'm showing for this particular study, we actually made some modifications of our typical model setup, including double the simulation domain. This is because especially for strongly magnetized planets, the interaction region would increase. So this enlarged simulation domain would minimize any impact from the outer boundary. We also increased our video resolution to 5 kilometers in the ionosphere to better capture the ionospheric structure. In total, we have about 2.4 million cells in our simulation domain. One last thing I want to mention is that for this study, we also changed the crustal magnetic field that we normally use for Mars to a planetary magnetic field. So we did a total of 4 sets of runs as illustrated here. Each set contains with 10 different dipole cases with dipole strengths ranging from 0 to 5,000 nanotesla. And these values are field strengths on the surface of the planet in the equatorial plane. Also, we assume the dipole moment pointing southward, same as the Earth, but without any tilt. The first 3 cases are all for solar maximum condition, but we vary the IMF orientation southward, northward, and Parker spiral. As we all know, for strongly magnetized planets like the Earth, IMF orientation could play very important roles. The last case is to examine the impact of solar cycle condition. So it's the same as set 3, except this is for solar minimum condition. So how does the global interaction change with different dipole strengths? Here we use set 1, a few cases from set 1 to as example to illustrate the variation of the interaction from the global scale. What plotted here are contour plot on the top panels, contour plot of plasma thermal pressure with white lines for magnetic field lines. On the bottom panels are contour plot of planetary plasma number density on the log scale. As you can see here, as we increase the dipole strength, the interaction region increases significantly. Another important thing to note is that for weak dipole cases, the plasma is mainly escaping from the tail region, while for intermediate magnetic field strength, dipole strength, as you can see, the plasma are actually mainly flowing out from the polar region. Of course, for the really strong cases, as you can see, the plasma density, especially in the outer magnetosphere, is very low because this interaction region is fairly high. Another thing I do want to point out is that please note that kinetic processes such as wave-particle interaction are not included in our model. As Alex mentioned yesterday, that those wave-particle heating could play a very important role in enhance the ion outflow from those strongly magnetized planets such as the Earth. The model result for strongly magnetized cases may require extra caution because of the model limitation. How does the ion escape rate vary with planetary magnetic field? Here we plotted the results of ion escape rate as a function of planetary dipole field strength for O plus density in green, O2 plus density in red, and the total planetary ion species in blue. As shown here, we can roughly separate the domain into 3 different regions. For weakly magnetized cases, we see the ion escape rate is pretty much constant, does not vary much with dipole field strength. For intermediate cases, there's enhancement of the ion escape rate, especially for heavy planetary ions, O2+. You can see a large increase of O2+ ion escape. For strongly magnetized cases, there's actually a fairly sharp decrease of the ion escape rate. But again, as I mentioned, result for those strongly magnetized cases may require extra caution due to model limitation. So next, we will mainly focus on field strengths less than 1,000 nanotesla and look into more details about this interaction process. What plotted here are pressure profiles along the subsolar line for different dipole cases. So there's actually 3 different pressures play important roles in control the interaction process, including solar wind dynamic pressure, which is plotted in red line here. That's the incoming force from the solar wind. And then 2 other forces, which are internal, including the ionospheric thermal pressure. This is this blue line here, close to the planet. And then the purple line shows the planetary magnetic pressure. The relative importance of this ionospheric thermal pressure versus planetary magnetic pressure actually determines whether or not this is an ionospheric dominated interaction or a planetary magnetosphere dominated interaction. To look into more details about the relative importance of the ionospheric pressure and the planetary magnetic pressure, we zoom into the region close to the planet. As you can see clearly, for 20 nanotesla case, the planetary magnetic pressure is almost negligible compared with the ionospheric thermal pressure. So this is clearly an ionospheric dominated interaction. The transition starts from about 50 nanotesla. As you can see here, planetary magnetic pressure, as shown in the purple line, is roughly about the same as the ionospheric thermal pressure. And when we increase the dipole field to more than 100 nanotesla, this is clearly a magnetospheric dominated interaction. There's a clear region formed very close to the planet, which is the planetary magnetosphere. Of course, this region increased with dipole strength. We also look at the ion density profiles as a function of altitude for different dipole strengths. What's shown here, the blue line, O2 plus density, and the green line, O plus density. As you can see here, for weakly magnetized cases, the ion density profiles pretty much stay the same. The changes really became significant when the dipole field strength increased to about 500 to 1,000 nanotesla. As you can see here, for 100 nanotesla case, the O2 plus density drops very sharply to almost 0 near about 400 kilometers altitude. While for higher dipole cases, the density of those ion species actually extends to very high altitude. This explains why for intermediate cases, we see a significant enhancement of the heavy ion O2 plus. Okay, so um, another question is whether or not the trend we found for the southward IMF also applicable for other IMF orientations and solar cycle conditions. To answer the question, we plotted the normalized mass loss as a function of planetary dipole field strengths. So they start from 1 with no dipole field. As you can see, for different IMF orientation with the green line shows southward IMF, as we discussed already, and the red line for northward IMF. The light blue color are Parker spiral, and the blue color here is also for Parker spiral, but for solar minimum condition. So even though there's some similarities in the general trend, but the detailed relationship between different IMF orientation and the solar cycle conditions are actually quite different. On the right, it's basically the same plot, but on a different vertical scale. Here is total mass loss rate in kilograms per second. Again, this is of course not a log scale, so it looks a little bit different. But yeah, what's striking is that for all the cases, for all the different dipole field strengths, as you can see, southward IMF seems to produce the highest ion escape rate, while the northward IMF produce the minimum ion escape rate. This is expected as we have learned from the Earth observations. As a summary, the impact of planetary magnetic field strengths on ion escape rates is calculated using a multi-species MHD model under different IMF orientations and solar cycle conditions with current Mars atmosphere. Our model results clearly show that the detailed relationship between ion escape rates and the planetary dipole field strengths depends on the IMF orientations, as well as the ionospheric thermal pressure controlled by solar EUV flux. In general, we found that the total ion escape rate does not vary much for weakly magnetized cases, increase for intermediate planetary dipole case, and decrease quite sharply for strongly magnetized cases. But the model result for relatively strong planetary dipole cases may require extra caution due to model limitation, as I discussed. At last, I do want to point out that these 40 cases that I show only cover a very small portion of the widespread parameter space. Other parameters, such as solar wind dynamic pressure, which come up quite often in previous sessions, could also play a very important role on the relationship. Of course, the neutral atmosphere, in our situation, we use current Mars atmosphere. Different atmosphere could also maybe have some control on the relationship as well. Those will be subject of our future work. So that's all I have. Thank you very much for your attention.
All right, thank you. Are there questions? Okay, so a couple just popped up. So the first is, what is the difference in background neutral density and calculated ion density between solar min and solar max?
Yeah, that's a good question. Yeah, so for the background neutral density for solar maximum and solar minimum are used based on previous model results. Basically, for solar maximum condition, the neutral density is relatively high, while for solar minimum condition is relatively small. Another difference is for solar maximum condition, we have a higher EUV flux, so the photoionization rate is also slightly higher. So as a result, for solar maximum condition, we have a larger ionospheric thermal pressure as compared with the solar minimum condition. So I would say, for solar minimum condition, because we keep solar wind dynamic pressure the same, so for solar minimum condition, because the ionospheric pressure is lower than solar maximum condition, so the planetary magnetic field would expect to play more important roles.
All right, thanks. I think this next question you also just answered. Have you looked at the effects of solar EUV, and is that the difference between your solar max?
Right. That's yeah. We try to answer the question by using comparing our solar maximum condition and the solar minimum condition, because the EUV flux will make changes on the photoionization, the ionization rate, and also change the ionospheric thermal pressure, which have some control on this interaction process.
Okay. So could you please comment on the general limitations of the fluid approach at the topside ionosphere and magnetosphere?
Yeah, that's a good question. So, the limitation of the fluid approach, of course, is, we assume that all the plasma is following, the magnetohydrodynamic model, right? So it's basically, we assume the plasma is magnetized, or, the so-called frozen in condition. I actually think it's not doing, a very bad job in describing the outer part of the magnetosphere. As you see, there's a lot of MHC model for Earth's magnetosphere, and they all seem to agree with the model, with the observation fairly well. But of course, they need to couple with, kinetic processes with, different models in order to reproduce the kinetic processes that also play like the ring current or the conductivity of the ionosphere. So there's a lot of limitations in the MHD model because the fluid assumption. But I do think, especially in the outer magnetosphere, it's actually doing a fairly good job. It's describing the interaction with the solar wind.
Right, and then up to 100 nanotesla, the escape rate is similar between Parker's spiral and southward BZ, while the latter becomes larger for larger dipole strength. Do you see any difference in magnetospheric dynamics below and above the 100 nanotesla dipole strength cases?
Yeah, that's a good question. I haven't looked into details about the detailed dynamics, but I did look at the pressure profiles for Parker spiral and northward IMF as well. Actually, maybe I can go to this slide here. Yeah, this is for different IMF orientations, southward, northward, and the Parker spiral. As you can see, the interaction process is actually quite different especially if you zoom into the regions closer to the planet. For southward IMF, because of the reconnection, the regions dominated by planetary magnetic field is actually limited to this very small region, while for northward IMF and Parker spiral, they actually, the induced field is actually on top of this planetary magnetic field. So they actually enhance the magnetic pressure very close to the planet. But again, the flow pattern could be very different, especially for northward IMF case. That's also why the ion escape rate is the smallest for this particular case. But there's a lot of details to be looked at to get a deeper understanding on what exactly the IMF condition is changing the dynamics and also control the ion outflow.
Okay, great. I just wanted to say we're moving into the last 6 minutes or so of our session. So I'm gonna open it up if people have questions for any of the speakers or want to make some more general comments. They should feel free to do that. So there's one more question for you, Yunjing. Is the solar EUV only providing ionization, or is there a heating efficiency as well, giving you a source for the energy equation?
Yeah, that's a great question. Yeah, the solar EUV provide both ionization and also heating to the plasma through photoelectron heating as included in our model.
Okay, thanks.